2.5 is about zeros of polynomial functions. So again, zeros are just the same things as roots or solutions, which are the x values of the x-intercepts. And again, what we're trying to do is factor. We're trying to factor these higher degree polynomials because if you know your factors, then you can find these roots or these zeros. So in order to factor these higher degree polynomials, this is a tool that we're going to need to use. It's called the the rational zero test. And what it allows us to do is find possible roots, because in this chapter we're not going to be given our roots. We're just going to have to find our possible roots, and then we'll have to determine the difference between our possible and our actual. And what that will lead to is being able to just be given a function like this and factoring it. So again, rational numbers, all they are two integers or whole numbers expressed as a quotient. Okay, so it's just a number over a number. 3, for example, is equal to 3 over 1. That's a rational number. Same thing with like 2/3 or negative 2/3. Okay, so rational numbers, all they are their fractions. Rational zeros, then, of course, are going to be these rational x-intercepts, or x values of your x-intercepts. So here would be an example of a rational zero. And we would know that it would cross the x-axis at negative 2/3. Alright, so in the last section we were given a problem like number 49 where I worked with this in the previous video, where you would be given a function and given a root. So we would know, well, hey, I can go ahead and use long division. I know that x minus 2, because here's a root, so just slap it into your factor, which is x minus, and slap in your root. So then x minus 2 times something is equal to this x to the 3 minus 7x plus 6. And we were able to use either synthetic division or long division to solve for this unknown, right? So now, though, we aren't going to be given this. That is the situation. We aren't going to be given a root, so how are we going to be finding our factors? So again, what if I just said factor the function completely and I just gave you this? Notice the difference. Nice teacher gave you a root. Mean teacher didn't give you a root. So now you're going to have to rely on the nice rational zero test. So the way that, this should be using, sorry. The way that you're going to find those roots, you're actually going to have to make a list for yourself of possible roots. Now this list may or may not be values that are actual roots. So we're going to actually have to go back and find them. But for now, what you're going to want to remember is that all possible x-intercepts, or all possible zeros, are going to be given by p over q. Mind your p's and q's. P over q. And p, I like to think about as p is the pathetic number without a variable. It's pathetic and lonely. Okay, so p over q. P is going to be all the factors of the constant, or the pathetic lonely term, and then Q is going to be all the factors of the leading coefficient. So, for example, if I gave you that x to the third minus 7x plus 6, and I wanted to find all possible roots, then I'm going to do that P over Q. Here is that pathetic number by itself. What are the factors of it? Well, we have plus minus 1 times plus minus 6, right? Because we could take 1 times 6, or negative 1 times negative 6. We also have positive and negative 2, positive and negative 3, because 2 times 3 could get us 6, or negative 2 times negative 3 could get us 6. Alright, and then on the Q are just all the factors of that leading coefficient. So you're going to look to your leading term once again. Our leading term told us so much about end behaviors, and they're also going to tell us now about possible roots. So positive and negative 1, because you could take negative 1 times negative 1, or positive 1 times positive 1. So note that the combination and the mixture of these will lead us to this list of all possible roots. Again, I did, once upon a time, as the nice teacher, I gave you a root. So note that that is one of our roots. There it is, but we just have to now find it. So how are we going to identify that that's one of our roots? Well, what we can use is to find actual or real rational roots of a polynomial. What you're going to have to do is use synthetic division. Okay, so you can use synthetic division to find your actual roots, because it's the quickest way to see, hey, if I divided this by this root, so let's go ahead and try it. We have we have I'm going to need a 0 because here's my x to the third, here's my x to the second. We're going to need negative 7 because that's the coefficient of my x term. And then we have that pathetic, lonely 6. Okay, so we're going to pull this down, 1 times 1, and then we're going to add. Okay, take this result times our root, so we're going to get 1, and then add, so negative 6. And looky there, we did get a good, on the first try, we got a good root. So here we did find that x equals 1 is a root because it leaves no remainder. Remember, for example, if we had like 9 divided by 4, if you divided that, which we would get 2 and then 8 and then we got a remainder, we know that, hey, 4 is not a factor of 9. So same thing as if you do this division process and you get a remainder, we know that it's not a factor. But since we didn't get a remainder, we know that it is. So I can go ahead and say that x minus 1 is a root. This is the result, or the multiplication. This times this is going to get my full degree 3 polynomial. So here's the remainder, x to the 0, x to the 1, x to the 2. So now x squared plus x minus 6. Okay, and now if we wanted to, we can go ahead and factor this completely. X plus 3 and then x minus 2. Okay, so there are 3 other roots. X equals 1, x equals negative 3, because if you set that factor equal to 0, if this whole thing we set equal to 0, we would set each factor equal to 0, and we would get these x values of our x-intercepts. So note, we were given this, nothing else. We were able to use that p over q method to find all possible roots, and then we had to use synthetic division to come up with what are the actual, by making sure that you do not get a remainder. Alright, graphing calculators are allowed to shorten this search process because when we use a synthetic division like this one, you can see we had a lot of roots that didn't work. The only roots that worked was this one and this one, right? So had I tried negative 1 out here, we would have gotten a remainder. It wouldn't have worked. So I would have had to cross that out, try something else. The thing is, if you add a different a to this process, like for example, had this been 2, then what you would have is plus minus 2 as well, and you would have to take all of these, so this would add an assortment more to your possible list, right? Because then you would also have I'm just going to have 1 over 2, we would have negative 1 over 2, 1 over 1 would have still gotten us just 1. 2 over 2 would still get us just 1, but now here we also have this 3 over 2, we have negative 3 over 2, and then 6 over 2 would have gotten us just 3, but here we have a long list of possibilities and it gets a little bit ugly. So using your graphing calculator and seeing the graph visually can shorten this process, and I'm definitely okay with you using the resources. So you can kind of check to see whereabouts the x-intercepts are on that graph, and you can check to make sure that they are by using that synthetic division. Alright, let's look at number 8. Okay, so number 8 is what they ask us to do is use the rational zero test to list all possible. So I'm going to just go ahead and list all possible right off the bat here. So again, I'm going to have the all possibles are going to be the p over q, mind your p's and q's, and that pathetic 16, I'm going to want to figure out the factors of that little lonely number. So we have 1 plus minus, right? We also have, that goes in pairs with 16. We have 4, let's go in order. 2 plus minus, and then we have all plus minus 8 to pair with that. And then we also have 4 times 4, right? So those are all factors of 16. And then we only have plus minus 1. So our list of all possible, you can do the plus minus, but I'm just going to do them all out. That's a 4. Negative 4, negative 8, 8, 16, negative 16. Alright, so now it does say use the graph, so you could easily type this into your calculator and look on it on your calculator, but otherwise they have this in your book, and what you can kind of do is check, oh okay, here's one of my roots, so x equals approximately, now we're going by threes, I would say negative 2, x equals 2 and x equals 4, and then you're just going to have to check these using synthetic division. So 1, negative 4, 16, and then negative 2, and you're going to see that it works. We're going to bring down that 1, multiply that result by the root, so negative 2, add what you got with that product, so we have negative 6, multiply that by your root, we get 12, add, so we're going to get, what is that, 8, and then multiply, we get negative 16, add, here's our remainder. So now we know that x plus 2 times, and then here's x to the 0, x to the 1, x to the 2. We just broke down this degree 3 with division, so it's going to now be decreased to a squared or a degree 2 polynomial. So we have x squared minus 6x plus 8, and I'm going to hope that I can factor this. I certainly can. X plus 2, x minus 4, which there that was, and then x minus 2, which there that was. Alright, here is your homework. Go ahead and get practice on that. Big hint on number 22, because you are going to find that there is no pathetic number by itself. And truly, we do still love that pathetic number, but it is pathetic. The one other thing is, you're going to have to watch out because complex numbers may appear. There is actually one theorem that I'm going to put out because it just sounds really important and we need to. The fundamental theorem of algebra. Sounds important, right? This is on page 150 of your homework assignment, and it says if f of x is a polynomial of degree n. So we have a polynomial f of x of degree n, okay, where n is greater than 0. So that degree, it's like a degree 1, a degree 2, a degree 3 polynomial. Then we have at least 1 0 in the complex number system. Okay, I would like you to think about what exactly that means. So we're going to try to interpret, because again, this sounds really important, right? And what does this really help us with? I would like you to consider that. All right, and remember, what is the complex system? I'm just going to remind you, a plus bi. What is this really saying? Okay, and you're going to have to kind of watch out for this idea as you do some of these problems. All right.